This project outlines the load paths, design process and structural loads of a domestic shed. Part 1 requires us to design numerous structural members of a domestic shed throughout the use of design parameters assigned to us for this project. Part 2 takes it one step further and requires us to manually calculate different types of loads of a shed also given to us. We're then asked to utilise a computer application named SpaceGas, where all calculations are re-evaluated to compare which calculations are more effective. On the right, figure 1 shows the structural elements of a shed. Loads. This presentation will investigate the different types of loads found on the columns and beams throughout the domestic shed design. A dead load can be described as a permanent or static load which remains constant over a large period of time. A live load is known as a temporary load of force that continues to move throughout the structure. A wind load can be classified as any pressure or force that the wind exerts on a building. An earthquake load is where the force of the earthquake is applied both in horizontal and vertical directions. And lastly, a snow load, which affects the vertical structures in the building as it falls above the structure. This slide shows the superstructure design parameters and the dimensions of the shed and the wind region which was given to us. The span is 9 metres, height of the eaves 8 metres, shed length 12 metres, base spacing 6 metres, roof pitch 5 degrees, and we're in region B, which is intermediate. The rest of the design parameters are shown above. We were given terrain category 3, which is TC3, which is where there is a terrain with numerously closely spaced obstructions, which is suburban housing or a lot of industrial estates. From this terrain category, we can then identify the selection of design wind speed. So the serviceability limit state, which was 39 metres a second, and the ultimate limit state, which was 61 metres a second. This then helps us identify the wind classification, which is N4. Limit state equations. In this slide you can see the serviceability limit state equation and the ultimate limit state equation. From the serviceability limit state equation and the ultimate limit state equations, we can now find the equations of the roofs and the walls. From the equations that have been identified and found, we can now design the bracing system of the first shed. Next comes the type of connections that connect the beam and the column together. Firstly, we have a simple connection and a rigid connection on the right diagram, and on the left you can see a beam to column connection. There are 4 main types of beam and column connections seen below. Firstly, a shop welded cleat. Secondly, an end cleat. Thirdly, double angle web cleat and seating angle, as seen in A, B, C and D. In the part 2 calculations, firstly we are asked to find the dead load of the shed, which consists of the roof sheet, ceilings, insulation services, purlins and the rafter weight. We are also asked to calculate the live load of B1 and B2. This slide shows the wind load calculations, which uses the ultimate limit state and the serviceability limit state from part 1 of the assignment. Column 1 calculations consist of the dead and live loads for the column. The calculations below have a diagram to the side which calculates the construction loads, which is people and materials, the dead load of the structure, the live loads, which is people and furniture, and also the dead load of the lower structure. This slide identifies the live load for column 1. Because of the live load found, which was 256.66 kilonewtons, 200 UC 59.9 column design can be used as a safe for buckling plan. This is where the bending moment, shear force and deflection equations take place. Firstly, the shear momentum and bending moment of column 1. You must identify the tributary area, the total load, and then calculate the two bending moment and shear force equations. For the deflection, you must firstly calculate the critical load paths. Firstly, what must be done to create a space gas model, the X and Y numbers of the shed must be identified. Once identified on the left, you can now begin to create the model as seen on the right. In the purlin design calculations, the dead load must be calculated first. Next is the calculations of the live load. The wing calculations are done to see if the correct beams have been used to see if the purlins are safe. As you can see below, the load maximum deflection is safe. In summary, it can be deemed vital that the correct calculation must be made for the design process to be successful. It is very helpful with the use of space gas as it helps check if the calculations are correct. Beam and column design are very important in the building design stages as the safety of homeowners and people rely on it.